Welcome to Buildings and Beyond,
the podcast that explores how we can create a more sustainable built environment
by focusing on efficiency, accessibility, and health.
I'm Robb Aldrich.
And I'm Kelly Westby. Around here, when we think of air source heat pumps, we think of Robb Aldrich. He's a principal engineer, and he's been working at Stephen Winter Associates since 2000. Before that, he designed, installed, and commissioned solar electric and solar thermal systems. But now he's just mostly focused on researching new trends and technologies to make buildings more efficient. And we'll get to hear a little bit today about his research on air source heat pumps. Welcome to Buildings and Beyond, Robb. It's very good to have you here.
Thank you very much. It's been a while.
Yeah. We are obviously going to talk about air source heat pumps. And I guess my first question is, why are we talking about air source heat pumps?
So 20 years ago, like when I was in grad school or just out of grad school, like the electric heating was just anathema. It was the worst possible thing in the world. Because generating electricity only happened at like 35% efficiency, and then you know, much more resource efficient to burn fuels in buildings to get the heat from them.
Right. And that's, I think, what our clients are saying to us now when we talk about air source heat pumps.
Yeah, it could very well be. But it was 10, 15 years ago, I started looking at some of the specs of these kind of later, what was then a new generation of air source heat pumps, and saw some pretty staggering efficiencies at relatively cold temperatures, and it kind of blew my mind. So, I mean, a heat pump, I guess people probably know what a heat pump is, but a heat pump uses a vapor compression cycle to move heat from one place to another, from outdoors to indoors in the winter, and then backwards in the summer. Like your fridge moves heat from inside the fridge into your kitchen. This moves heat from outdoors to indoors to heat your home. And historically, heat pumps, air source heat pumps, which is what we're talking about today, rather than ground source heat pumps or water source heat pumps. Air source heat pumps have historically been used further south, where it's warmer, because they didn't used to perform very well at cold temperatures. So in Florida, lots of air source heat pumps. You know, when the temperature got down to 30-ish degrees or whatever, they switched over to electric resistance. And that didn't happen all that often, so it wasn't really a big energy hit. But up here, it would be a big energy hit.
We operate very often below that temperature.
Below 30 degrees, yeah. So this was something that fascinated me. I was kind of incredulous of the performance, you know, the rate of performance of these systems. So I was keeping an eye on it for the past 10 or 15 years. And watching how the products evolved, and really was interested to see if we could actually measure performance to see if they lived up to their hype, their ratings.
Oh, interesting. And kind of maybe this is a step backwards, but let's lay the groundwork a little bit. Can you talk a little bit about the terminology that we use around water source or air source heat pumps, and what the industry is calling things, what you like to call things?
Yeah, there's lots of different terminology that people use, and I don't pretend to be the authority on it, but I try to be at least consistent myself and do what I hear most other people do when they talk about it. So mini split is a term that you may hear a lot. And to me, a mini split means mini, small capacity, and split. So you have an outdoor unit and an indoor unit. So like a window AC is not split, it's packaged. Everything's in one package, you stick it through the wall and it cools inside. Great. So split means you have an outdoor unit and an indoor unit. And the outdoor unit, a lot of people still call the condensing unit. Because when you have an air conditioner, that's what it is. But when you have a heat pump, the condenser is actually inside in the winter and the evaporator's outside. So a lot of manufacturers call it the outdoor unit. So I try to also call it the outdoor unit. It's more correct.
But it can actually be inside sometimes.
The outdoor unit?
Yeah, and ducted to the...
No. The outdoor unit is going to be outside.
In VRF, sometimes we see them ducted to the outside in some commercial projects.
Okay. Gotcha.
But yeah.
So where right, you suck air right in and out. Huge louvers or fans.
Right.
Okay.
Yeah.
Gotcha. So it's almost outside.
Almost outside. Very close.
Gotcha. But on the mini split front, sometimes I think quite a few people use the term mini split only to mean ductless systems. So most people are familiar with those. You'll see the cassettes usually high up on the wall. They're very common everywhere else in the world except the US, but more and more common in the US. No ducts. It just sucks room air from the top and blows out the conditioned air from the bottom. So some people when they say mini splits, they mean ductless, but you can also have ducted mini splits, or what I call ducted mini splits, which have short lengths of duct to deliver air to a couple rooms.
Great. And then now that we've gotten all that under our belts,
and VRF. You mentioned VRF?
I did.
Should we
threw that out
clarify there?
Yes, please.
So this is even more annoying because the terminology doesn't necessarily reflect the reality. So VRF stands for variable refrigerant flow, which usually is used to refer to larger systems than the residential heat pumps that we're going to be talking about today. So you'll see 6, 8, 10 ton systems. You'll see several, gang together on the roof of a big building with, dozens of fan coils spread all throughout the building. And VRF is larger systems that can handle much longer pipe lengths. Every fan coil indoors has a expansion valve. It's a lot more versatile and bigger capacity and more versatile. The small heat pumps that I've been looking at for single family, really all kinds of buildings, but small capacity, like 5 tons or less, often much less, often like in the 1 ton range. They have variable speed compressors, inverter-driven compressors, and therefore they have variable refrigerant flow.
Wow.
But they're not called variable refrigerant flow. They're called inverter-driven heat pumps or a whole bunch of other terms, but variable speed heat pumps. So VRFs are usually not called heat pumps, even though they pump heat, and inverter-driven heat pumps are not called VRF, even though they have variable refrigerant flow.
Great. And now that that's super clear, you brought up clear as mud. I think someone around here used to say. You brought up inverter-driven technology. Can you talk a little bit about inverter versus single-speed 2-stage, kind of how that technology has evolved?
Yeah, I guess the history of it I can't speak to too much. I think it was in Japan. I think it might have been like 30 years ago or something. So the inverter refers to part of the electronics. Here's my simplistic understanding. But power to these units gets converted to direct current and then inverted back to alternating current at the frequency you want the compressor to operate. So if you operate the compressor at varying frequencies, you can deliver different amounts of refrigerant flow and different capacities, depending on what the control system wants, depending on the load, depending on whatever the control algorithms are calling for. So that's where the term inverter comes from. And there are some efficiency benefits when you compare it to single speed or even 2-speed, because you basically have, in a lot of these systems, you have the same coil area, the same heat exchanger area, but you're moving, half the refrigerant at part load. So you're using much, much less electricity to move that refrigerant, but with still a pretty large coil area, you can get pretty good efficiency. And the other way that it helps is in cold weather. They can kind of overclock. It's probably not the right word, but when you need a lot more heat, the compressors can run at higher speeds than they normally would under, single stage, 60 hertz, whatever. So they can run faster, deliver more heat at really cold temperatures. You'll take an efficiency hit when they're working that hard, but it really can provide. It's pretty impressive how much heat they can provide at cold temperatures.
Right. And I think part of it too was about matching the load in the space more closely, right? Not having to kick on and kick off the compressor?
Not cycling.
Right.
Yep. There are some comfort benefits, maybe durability benefits, maybe energy benefits associated with, less cycling.
Right. And sort of speaking a little bit to that efficiency, can you talk a little bit about rating systems? People say COP, they say HSPF. What are the differences? Who's testing? And are these the right tests to be applied to these new-ish to us inverter-based?
That is a big topic. And so COP stands for coefficient of performance, which is energy out over energy in. It's basically efficiency, but you would hope that the COPs are actually greater than 100% because you're moving heat from one place to another. You're not converting heat. So, you want to see COPs, in the 3s or 4s or, the higher the better, depending on the application. It depends. HSPF stands for heating season performance factor. It has units of BTUs per watt hour. It was developed initially. It was developed to kind of duplicate SEER ratings for air conditioners, I believe, and then used for heat pumps back at like 30, 40 years ago. When heat pumps were only used down south, they didn't have a lot of cold weather, and it was pretty much single stage equipment. And the HSPF rating, the calculation procedure, really makes sense for that kind of equipment. For the newer equipment, it really doesn't make sense. I hate to throw stones because it's a lot easier to criticize things than to actually develop a good standard. But it's
we
not.
We have really good windows here, though, so it's fair.
Oh, yeah? Nice. HSPF for inverter-driven heat pumps are pretty worthless. The number is pretty meaningless to me. So what I do, and there's a lot of reasons for that, and some folks at CSA in Canada are trying to develop a test procedure that's more appropriate and reflects real world performance better for variable speed systems. I mean, it's really hard. It's really hard to rate. It's really hard to test because everything's variable speed. The compressor's variable speed. All the fans are variable speed, and you can only test at steady state, really, or well. Maybe not, but that's how the tests are done at steady state. So how do you do that and to make it reflect real world performance? And they haven't figured that out, but hopefully it's coming.
Great.
So I look at the manufacturer literature and I look down at like the COP at the design temperature, at my heating design temperature or cold design temperatures to see what the capacity is, to see what the efficiency is from the manufacturer literature.
Great. That's a good recommendation. And speaking of these rated COP on the unit and the rated capacity, didn't you do a study in 2012 about how these things are actually performing?
Yeah, that was fun. That was a small study. That was like 10. We monitored 10 ductless mini split heat pumps in single family homes around New England. It was sponsored by the Department of Energy. And we partnered with Efficiency Vermont on it, and we monitored. Like I to that point, I hadn't seen, for my taste, rigorous enough assessments of field performance. And again, they're hard to monitor because everything's variable speed, especially the airflow on the indoor units. So we monitored return temps, supply temps, and airflow in real time. And that airflow varied depending on fan speed, depending on how soiled the filter was, depending on the little vane positions that direct the air up or down. So it really varied a lot. So monitoring airflow allowed us to calculate more accurate heat delivered, and then also we monitored electricity consumption. So from that we could get the COPs.
And you mentioned there were not so rigorous studies before. What was missing from those?
I think mostly the flow rate. I mean, it's easy to monitor electricity consumption. It's pretty straightforward. So quite a few people had done that. Some people monitored return temps and supply temps and not flow rate. Like they looked up the literature flow rate values for the heat pumps and assumed that was what was being delivered.
So they were assuming that the COP was wrong, but that the flow rates were right.
That's kind of like, well, there's also a COP. You can just look at the literature and find a COP. But it's hard, and we went around and around and around on what the best way, the most practical way was to measure flow rate, and we were lucky to get the funding to do it. It was pretty interesting.
Great.
And the findings were concerning at first. So it was a cold winter that we monitored. I got it 2012, 2013, or 11, 12. Actually, I'd have to go and look and see.
We'll have the study in the show notes.
Thank you. We'll put the study in the show notes. I will put the study in the show notes. So the average COP of the systems we monitored was 2.0, which was lower. I mean, I think I was expecting closer to 3. For heating.
Based on the literature?
Largely based on the literature. And so it was sobering. But the other thing was that it ranged all over the place.
Right.
We had one system that had a COP of 1 for the whole winter. And which floored
Meaning
me.
electric resistance heat.
Pretty much, yeah, why not? Yeah, you just should have had electric resistance heat.
Right.
And we had some that were really good, in the mid 2s. So so the range of performance was pretty staggering.
Right.
And that was really concerning. So many people told me that our study is bogus, it's flawed, it's all, so many people dismissed it. But we went back to...
Were there some specific complaints?
That it was wrong?
Yeah.
Yes.
Okay.
They're way too low. These efficiency numbers are way too low. They can't possibly reflect real numbers.
Okay. Not like the way that you measured CFM was, inaccurate.
Yeah, they didn't get into detail. We probably tried 20 different methods to measure flow rate from these systems. And there's one friend of mine who we went back to his house like 5 times. Thank you, John. Thanks again. He's an energy geek also, so I think he was happy to help out. But it was we did our due diligence, so I was pretty confident that it wasn't crazy. But the other thing we found was that the capacity, the heat output, pretty much did match manufacturer specs. It was the efficiency that was off for some of the systems, quite a few of the systems.
Okay. And so are they still calling you up and telling you to fix your study, or?
No, because there have been other studies which found similar things. So I passed the buck to the people that did the other studies. A few years later, there was a study, the Massachusetts Utilities hired Cadmus to do an evaluation of much more, 100-ish systems in Massachusetts homes, and I think Massachusetts and Rhode Island homes. And so they used a similar method where they didn't measure flow rate, they measured return temp, supply temp, and electric power. The winter that they did this evaluation was the record-breaking snow winter, the most snow ever recorded in Boston forever. It was very cold, very snowy, and they, in 100-ish, I hate talking about other people's reports, so we'll
link it as well.
Link it. But from my reading of the report, that first winter, that incredibly cold winter, they found average COP of 1.7 of all the ductless heat pumps installed. Okay. Which is even lower than what we've found. But again,
maybe
the range,
maybe somewhat aligned compared to outdoor temperature, something like that.
Yeah. But again, huge range of performance. Some systems were performing great. Some systems were horrible, absolutely horrible. And so they continued the evaluation for another winter. Again, this is my understanding. And the next winter was like an absurdly mild non-winter. And the average COP went up to 2.5. So a big difference. But there again, staggering range in efficiencies and performance. So this got us thinking about, what, obviously these systems can perform to their specifications, just a lot of them are not. So, yeah.
What's going on? So did you find that there was a particular manufacturer that was problematic, or what did you find? No particular manufacturer seemed to be bad. In general, and we haven't figured it all out, but I think we know some things, and some are common sense. One of the most common sense features is these things suck heat from the outdoor air. If they're buried in snow, they cannot suck heat from the outdoor air. And that seems obvious and stupid. Right. It's not. There were so many of these systems that were buried in snow, or especially when we had like 5 feet of snow on the ground, or like underneath drip edges, on the side of the house, underneath the drip edge without a gutter, or the gutter fills up and freezes, and ice drips down and encases the heat pump, the outdoor unit, in ice.
we saw that in our small study, and they saw it in the bigger utility study. That's common sense would say that you should not do this, but
So mounted above the area median snowfall, sort of that
mounted, get
number.
it up above the snow, right? Which might mean pretty high. Especially in northern New England, I see them mounted on the sides of buildings, 4 or 5 feet up, above the snow, not under a drip edge, or if it is, or maybe even if it isn't, protect it with like you'll see a lot with little hats on them to shed the snow and ice and rain so that the evaporator doesn't freeze out there. So that was probably the most common sense thing we found that
It's an easy one.
explained the poor performance. Sizing was another one. It's sizing the systems so that they meet the load better. They're better matched to the load. Tends to lead to better efficiency, and that's for ductless systems more. What we found in some cases, the ductless heat pumps, if they were really oversized, the indoor fan coil was always in low speed. The fan was in low speed, and that kind of crippled your capacity and efficiency. So it wasn't. It underperformed.
Yeah, and I thought that because these things vary in terms of the compressor can vary to meet the load, that oversizing wasn't as much of a problem. But it's interesting to hear,
Yeah, I think it's with ductless. So if you went in and you took that same ductless heat pump and took the fan and stuck it on high all the time, you might not see that problem. But that's a lot of airflow. It can be cool. It can be loud if you always have your indoor fan coil on high. Actually, I saw a study, which I can try and link to, that did that. They did a few nights with a heat pump, the fan in auto, and then a few nights the same heat pump, they put the fan too high, and they saw like a 40% increase in the COP.
Oh,
and
wow.
they just put that indoor fan speed to high. So that was a big deal.
You mentioned the outdoor unit. Is there anything in terms of the indoor unit where it's located, or?
Return air temperature seems to be a pretty big deal. These things were initially developed for cooling. Again, I'm talking about ductless. So put them high on a wall. And also above head height, so you're not going to whack your head into them. That's important. But the warmest air in a room is going to be out by the ceiling. So that's the return air for most of these ductless heat pumps. So we saw return air's temperatures of high 70s, 80s pretty regularly in some of these homes. And with that high return air temperature, you're going to lower your capacity and efficiency. So, yeah, a ducted system where you can suck cooler air from a more appropriate place, or many manufacturers make like low wall, like floor mounted kind of radiator sort of profile heat pumps, which may make more sense in a heating dominated space.
Interesting. And one thing that we find, I know in VRF mostly, in some of the commissioning projects that we've done, is we'll get a low discharge air temperature and we'll find out that there's a issue with refrigerant charge.
Oh my God, yeah. That COP of 1, which I was like, we must have done something wrong. I talked to another a researcher who had said, yeah, I'll bet you anything that's overcharged. Yeah, charge is important. I mean, it always is important. And I don't, again, with variable speed equipment, it's really hard. It's harder, I should say, to assess the charge with variable speed equipment. You can't, checking superheat or the common methods you use to check charge in single stage equipment. Everything's variable speed. The indoor fan's variable speed, the outdoor fan's variable speed, and most importantly, compressor's variable speed. So it's harder to do those checks. So weighing in the refrigerant accurately when you install it is the way to do it.
So measuring the line lengths, testing the pressure testing, vacuum, and then adding the right amount of refrigerant. And some of them are like pre-charged for line lengths of between X and Y. Okay.
So, but pay attention to that.
Right.
And if you don't need to add any, don't add any. And if you do. I mean, follow the instructions.
All right. So if we're back here in 5 years, what are we going to be talking about here? We're going to be talking about some other studies that we didn't get to talk about. I assuming because we ran out of time. But
I do want to say that a lot of these kind of best practices are outlined in some pretty good NEP documents. NEP is the Northeast Energy Efficiency Partnerships. And they have a good specification that'll let you know if you want to use a heat pump in a cold climate, what to look for, what the COP to look for, et cetera. Also, they have some heat pump selection guides, so for a particular application, how to think about what kind of heat pump to select, or is the heat pump going to be appropriate for your application?
Right.
And
because
also,
it's not necessarily the appropriate in every scenario.
No, I wouldn't say so. Especially, well, I mean, it depends what your goals are. I mean, if you have really big loads, then going back to fuel-fired systems is still going to be the lowest cost and maybe most practical way to meet it. But another part of the reason we see more and more heat pumps is because loads are getting smaller and smaller and smaller, especially with new construction efficient buildings. NEP also has a kind of guideline for quality installation, which talks about a few of the things that I mentioned and more things. So that is definitely a good resource. So I would refer you there. And also, I talked about the big utility study, which had pretty cool results.
Mentioned another study. Let's talk about it.
So just recently, Vermont did a study of air source heat pumps, ductless air source heat pumps installed through their incentive programs. And they found really staggeringly good performance. Average COP for several dozen, I don't think it was 100, but it was 70-something maybe, I think. Average COP for, I think it was 2 winters, was 3.0, which is so much better than the other studies. And I think Vermont really, took a lot of these findings to heart. It's like, we got to make sure our systems are installed better.
Okay.
And I listened to a presentation from one of the guys at Cadmus that did the evaluation, and he said, the quality of installation was just so much better.
Interesting. He saw both studies.
Yeah.
Okay.
Yeah, he was doing both studies.
Right.
Yeah. So the quality of installation was so much better. And the users were so much savvier about their equipment and knowing how to operate it. I mean, one of the systems we monitored in Vermont, I looked out the window and there was the outdoor unit of the heat pump buried in ice underneath the drip edge. And I said, I don't think that's going to work very well. The guy said, well, it'll probably work again in April when everything melts. It's,
Who needs heat in the winter? Well, I'm glad you re-steered me there, Rob, because that is a much happier note to end on. And I think probably the manufacturers will be much happier with us to end on that note as well. And so I'm going to take back the question, and I'm going to say that in 5 years, we'll be sitting here talking about your new study on VRF systems, which I just want you to do.
Yeah, VRF.
That are, in 5 years, they're going to be performing perfectly because you'll have figured it all out, and we're going to figure out how to make them perform perfectly.
I have concerns about VRF systems. VRF systems are a lot bigger, a lot more complicated, a lot more joints where refrigerant might leak, for example. So I haven't yet seen good studies that show heat delivered and electricity consumed.
Right. Me neither.
Yeah. If anybody listening has, please
send it to us. Yeah. And actually, on that note, did you see any differences between having one indoor unit and multiple indoor units on the same outdoor unit?
No, I didn't. We only monitored one-to-ones, but the 2 Cadmus studies that I mentioned monitored what I call multi-split, where you have one outdoor unit with 2 or 3 indoor units. And yes, efficiency was lower the more indoor heads you had for the same outdoor unit.
Wow.
So and I've talked to a lot of contractors that say the same thing. Like, oh yeah, everybody knows that. Multi-splits are much more efficient. So one-to-one's the way to go if you can
afford all of those outdoor units.
They're not even that much more expensive. A 3-to-1 is kind of 2.5 to 3 times the price of 3 1-to-1s. Kind of.
Oh, okay.
Yeah, that's been the pricing I've seen.
Interesting. All right. Well, on that note.
All right.
Thank you for being on the podcast.
Thank you.
Thank you for listening to Buildings and Beyond. For more information about the topics discussed today, visit www.swinter.com/podcast and check out the episode's show notes. Buildings and Beyond is brought to you by Stephen Winter Associates. We provide energy, green building, and accessibility consulting services to improve the built environment. Our professionals have led the way since 1972 in the development of best practices to achieve high-performance buildings. Our production team for today's episode includes Dylan Martello, Alex Mirable, and myself, Heather Breslin. Thank you for listening, and we'll see you next week.